a pleasure to start this meeting here, and maybe especially after an interesting event we had at our institute this morning. You know that famous scientist, academician Ginsburg, last October 4th, there was celebration of his 100th anniversary, and because he spent a lot of time in Nizhny Novgorod. It was 1945 he arrived here, and he was the chair of one of the departments at Nizhny Novgorod, the time working State University, and spent this position 16 years. And actually, he was a parent of many directions of research at our institute. And this branch we are here today, it is one of actually his legacies for our institute. So, and I think that this direction, I mean, radioastronomy application to interesting events in the universe remains one of the most interesting topics also at our institute. So recently we don't have actually enough funds, enough abilities to support this research experimentally. Actually, it is a great problem now. I think Russian participants know for sure. Maybe foreign participants, they are not well acquainted with our situation, that in the recent 25 years, actually, just during the so-called new Russian time, we did not receive money from our government to support our infrastructure. Of course, we earned some money ourselves, and we took some money from our grants, contracts, and so on. But this process was not really regular, mostly chaotic. We understand that in radioastronomy, it is, in astronomy in general, it is very important to have infrastructure. You have to have telescopes to observe, you have to launch satellites to observe from the space, and it is very, very expensive. What we see now as a major tendency, trends in development of the science is that science more and more is done at big infrastructures. And according to some estimates in 10 or 15 years, more than 90% of new fundamental results will be actually received at these factories of fundamental science. And it's understandable because to know better the universe and also another world, you have to build instrument which is getting more and more expensive. So you build an instrument which provides you ability to investigate processes at nanoscale. But now you have to go to picoscale. It is more expensive. And only some collaboration of different countries, not speaking about university institutes, only collaboration of different countries, several countries, can provide this budget. So infrastructure is getting more and more expensive. I know that in Europe there are more than 30 projects on the European roadmap of research infrastructures. And well, some of them are available for us, some are not. And I know that our scientists are now still fighting to be part of South European laboratory in Chile, and it is also a kind of possibility to use this infrastructure, but not not yet so successful. I would like to, if I have a couple more minutes, I would like to tell a story about, and this story also is connected with some kind of development of big research infrastructures. A couple of months ago, we visited Lund. Lund, very famous university in Sweden, and also they are engaged in two very big European projects. And there was a discussion of how a small country can issue enough amount of money to build two big research infrastructure. Of course, there is support from Europe or other countries, but the host country typically pays more money for this. And there was an interesting answer from these people. They refer to the history, and it was the history of astronomy. It was a story about TIFR, well-known Danish, and at that time Denmark actually includes South Sweden, so actually one country, Denmark. And the king of Denmark, you probably remember Shakespeare, the king of Denmark was a very powerful person. And that time, just by some reason, the king of Denmark, it was Friedrich II, donated a lot of money to Tycho Brahe. And Tycho Brahe received some isolated island, he built some observatories there, and actually succeeded in much more exact results and trajectories of planets, stars, and so on and so on. And they calculated our colleagues from Lund, they calculated that the money spent by the king of Denmark to develop astronomy was actually comparable with the annual budget, one annual budget of the country Denmark. It was huge, actually a huge amount of money. And why the king decided to do so? Because Tycho Brahe replied to give this letter. It's very interesting work. So your majesty and so on. If you give money to build this new instrument, we can really predict the trajectories of stars much more precisely. And of course, it provides us for more exact information about horoscopes and also horoscope to your messages. So, you know, maybe it is just a kind of wisdom how to communicate with the government. Of course, you know better who Tycho Brahe was, more astronomer or astrologist, I don't know. But especially in a situation that the government, the people from government, I think that they are quite receptive to this information about the horoscopes. Well, so again, MARION astronomy is very important. So in our understanding, of course, we are lacking of access to big facilities, and research infrastructures are now very, very important. And maybe academician SHUSTOV, who is heading actually the team of Russian astronomers who advises now to our government what to build and where to build, will be successful in pursuing some of our goals of our demand. And I hope this meeting will help us to bring our research at least a bit higher, and maybe just based on the result of this meeting, academician SHUSTOV will recommend to our government what to do and what must be done first. So thank you.
I will do my best. Thank you very much.
Astro will be led by Ojha D.K from Mumbai. That is a Let's go. Thank you very much. Good afternoon, all of you. So let me first thank Wiebe for organizing this Russian seminar. And unfortunately, a couple of Indian participants could not come because of other commitments, but they will be connected through Skype, I guess. And the idea of, our idea of our speaking is that we have already this collaboration going for the past 5 years with Astronomy, Wiebe and other group. But the idea of this that after this meeting, we can have a more mutual strong collaboration. So these talks are actually meant to, for example, give an idea that what kind of collaboration we can do. For example, the thing which I am talking today is basically looking forward for next generation, some limited observations like ALMA and other things. And I know that there are a lot of experts are here who are using ALMA, so I will look forward for such kind of collaboration. So today I will be talking about episodic accretion which are happening in young Nova stars and how they shape the formation of these stars, particularly the planetary formations and these formations, and what is the role of outflows during early history of these Nova stars. So most of this work is done by my PhD student who has just submitted his thesis. Okay, so the outline of my talk is, so briefly I will talk about what are the open problems in star and planet formation, okay, and why these episodic accretions are very important in the early history of Nova star formation, and what are the physical mechanisms behind these episodic accretion, okay, and if time permits, so I will also show some of the new results where we have first time seen observationally that, of course, theoretically we know that accretion is connected to outflow because of environmental problems, but we have now shown first time that how observationally we can have direct evidences for these outflow accretion relationships. So if time permits, I will go to that result also. So this is the simple cartoon how the birth of Nova star formation can happen from dark clouds because of gravitational collapse, and then at this time scales you have the inside accretions and outflows which are happening because to conserve the angular momentum. And if you come to this time scale, which is roughly 3 million time scale, where actually the protoplanetary disks are forming, it is roughly the time scale, and then finally you have dissipation of the material due to outflows, and then you have a stable protoplanetary disk, and then you have central star like our sun. Okay, so in this talk, I am basically concentrating these two steps, which are very important in formation of Nova stars like our sun. First of all, the importance because of the planetary disk formation during this time scale, and the lot of mass which is gained by the star, which actually basically decide the final fate of the star, happens during these two steps, okay, where matter is accreted in an episodic formation. So when I'm talking about episodic accretion, means this is the time scale when these kind of violent activities are happening and where star is gaining its mass, okay, and that basically shapes all the history formation of the star like our sun. Okay, but things are not easy because we don't know many problems. For example, some of the open problem I will be discussing here. For example, one of the famous problem in star formation is about velocity problem, where basically there is a mismatch between the observed velocity function with the statistically expected velocity function. Okay, for example, if you see the like torus kind of star formation, if you count all the stars and calculate the velocity, you will find these are 2 orders or even more orders of less than what you expect statistically or theoretically. Okay, because if you see that if outflows and accretions are very static, for example, very normal, then whatever you see that whatever matter falling from envelope to disk should be transported from disk to the star. But that is not the case. What we see that sometimes accretion from disk to stars are very episodic and very high. Okay, so probably this curiosity problem can be solved by studying the episodic accretion. So that's why they are very important object. Then another thing which we don't know is like knots which we see in outflows, for example, propagating from low mass star. For example, there is a star here which is embedded, and you see the display, and you see these periodic knots which cannot be explained by just having a simple accretion which is going on from envelope to disk or disk to star. It needs something kind of episodic accretions in a periodic phase. So these knots can also be explained by this. Okay, and if you really go to our solar system, for example, this is one of the meteoroids. Okay, what you see here, this kind of structure which are called like CR, calcium, aluminum rich inclusions, or these conduits which are very famous in these meteoroids. Actually, they get heated up to like 3000 degree Kelvin, roughly around the melting temperature of these kind of things has been seen in meteoroids, and then they cool down. So to basically have such kind of high temperatures, you cannot form in a simple way in a solar system. You need something acting as it. Okay, so for example, this episodic accretion from the young nova stars actually can have produce such high temperature which can melt these kind of metals or inclusions in the meteoroids. So what we know that, and also if you do the radio dating of these kind of meteoroids, it has been found, if you calculate the age of these meteoroids, which is roughly comes out about the 3 million years, which is, as I said in the beginning, is roughly the time scale of the protoplanetary disk formation. So this is probably the episodic accretions can explain all these open problems. Okay, so probably we have this kind of direct observation, but things are not as easy. I will go along with this problem. Okay, so why we are so worried? I mean, why these episodic accretions are very important? For example, they are very important to understand the history of star formation. For example, like how the pre-main sequence of a star's evolution happens. For example, if the star is evolving, so this is roughly the HR diagram where you have effective temperature versus luminosity. So if there is no episodic accretion, what you see the evolution of the star in a simple track, okay, evolutionary track. But if suppose there are episodic accretions happening in the star, okay, you can see that how these tracks can be changed. Okay, so you see lot of changes. For example, this alpha parameter here is called accretion energy. So for different accretion energy, you can have different kind of evolutionary path, which means that if you are calculating the mass of a star using these tracks, you can have an error in the mass estimation. Okay, so it is very important to understand this episodic accretion, because ultimately you use these three main sequence tracks to estimate the mass, age, and SR. That is what we do. Okay. And another way which I will talk at the end of just before the end of my talk is about the planet formations. As we know that planet formation, for example, you see the snow line. Okay, snow line is basically the radius from the center star, disk radius, where actually the water or CO kind of molecules go below beyond the sublimation temperature. Okay, that is the snow line. And between the snow line, basically planets form because these ice actually get stick to the grains, and these sticky grains are very important for planet formation. Okay, so if there is no episodic accretion, we know that up to 5 AU you can form the planets like rocky planets. But suppose there are where these episodic accretions are happening, it can actually shift the snow line further away from the center star. For example, in case of like solar kind of mass stars, this snow line can be changed from 5 angstrom to 14 angstrom area. So which will basically prevent the formation of rocky planets. Okay, so it is very important formation of planets. So for example, in outbursts, it can really push this snow line. So this is very important to understand the chemistry of these kind of problems. Okay, and this can also produce gravitational stability in the disk. We don't know how the silicate is crystalline in the solar atmosphere. So there are many such problems can be actually explained by this episodic accretion. Okay, so what I will be talking about is, so what are the physical mechanisms behind this episodic accretion? Okay, and what is the nature of different types of these outbursts? Okay, are these outflows correlated with accretion? And what are the driving mechanism of outflows? So these are the couple of points which I will be touching. So just to give you an example, what is this episodic accretion? So there are these two classical examples in the literature which we call like FU Orionis or EX Orionis type of outburst. So FU Orionis, so what you see is basically this is a time versus the magnitude of brightness. So if a star is in a quiescent phase, okay, once it goes to the outburst phase, brightness changes. Okay, so this is basically the star has gone to the outburst. So FU Orionis has long outbursts, decade-long outbursts, and X Orionis has few months of kind of outbursts. So these are the differences, and amplitude of the magnitude change also varies between these kind of outburst sources. So we know there are two classical kind of outburst sources in the literature, but now we know that there are many intermediate kind of outburst sources between these two kind of classes. So these kind of outburst sources are ideal laboratories to test protoplanetary disk accretion and accretion outflows theories. Okay, so to understand this, so we started actually a very long program which we call MFPS program. So this is a very comprehensive long-term multi-wavelength monitoring from optical, near-infrared, radio. Okay, and we have selected a dozen of outburst sources which are known to us. Unfortunately, such kind of sources are only dozen of sources which we know. So therefore, it is very important to understand nature of all these outburst sources. So out of those dozen of sources, we have actually picked up two very peculiar kind of outburst sources called V1647 Ori and V899 Monoceros. Okay, and we actually monitor these sources for large number of nights. For example, 175 optical and 45 near-infrared nights. We are mostly using Indian facilities. We have a 2-meter kind of telescopes in India, and we have our own instrument which we developed in India. These are for near-infrared instruments, and then of course we have used our radio telescope GMRT. Okay, and also recently we have used very high resolution data using 11-meter short telescopes from South Africa. And apart from that, we also use archival data wherever these kind of sources have been observed. The thing is that if you want to understand the nature of such kind of sources, you need a large coverage as well as the filling factor of observations should be very high. Okay, so that's why this is called large monitoring program. Okay, so now let me come to basically to understand how these outbursts are happening. Okay, so basically these outbursts in young stars basically happening because of instabilities in the disk. Okay, so there are many instabilities models have been discussed in the disk, and most popular instability models are called thermal instabilities, when because of the accretion of the matter, disk gets heated, and because of the rise in the temperature, disk can be unstable. Okay, and all these kind of instabilities can be actually discussed based on the viscosity in the disk surface. Okay, and all these models are basically called famous models are called like alpha disk model, where alpha is the viscosity parameters, and these can be explained by a simple equilibrium S curve. Okay, this is nothing but this is the surface density of the disk versus the temperature. So when star is in quiescent phase, surface density is here at low temperature, but when there is an outburst happening, the temperature goes to the critical temperature where surface density also increases, and that can produce the instabilities because viscosity changes, which can actually effectively changes the opacities, and then it can ionize the hydrogens, so you don't have free electrons to give away. So it can actually make instabilities. Once disk is drained, okay, by these instabilities, then it comes back to the again to the original phase. So this is called famous equilibrium S curve. Okay, so you can actually explain all these kind of outbursts or instabilities by these kind of models. But now in literature, there are many other kinds of models have come. Okay, one of them is called gravitational stabilities because of the piling of the matters actually gravity can change and it can actually make this very unstable. And now more famous models are because of the magnetic activities which we call magnetorotational instabilities like MRI models. Okay, and also people have discussed that you can actually perturb the disk by the planets if you have heavy planets around the disk, which can actually cause these high accretion events. And there are some observational evidences for these. So all these models are basically viscosity dependent, but what is the most important in all these models is the time scales of these accretion events. So all depends time scale where basically you can drain the disk, then you can fill up the disk and such kind of stability you can produce. So it's very important to understand these time scales based on your observations. So basically viscosity is actually given by, as I said, this parameter called alpha, which is less than 1 to adjust this equation, and the velocity which is happening in the disk is like a sound velocity ch, and h is the height of the disk, which actually produced because of the turbulence and eddies in the disk. So you can actually calculate the height of the disk. So basically viscous time scale is nothing but this parameter tau is actually 1 upon alpha. Okay. So what happens that in case of when star is at quiescent phase, okay, you will have less viscosity, but when you have outburst phase, you have very large viscosity. So in these models, what they assume is that alpha is in outburst phase is always larger than the alpha at quiescent phase. Okay, so all these model requires, which means that if you, this is just 1 upon alpha, so time scale, so which means that all these models require longer quiescence than outburst. So if some star has gone in outburst, it should have a longer quiescence phase, then you can explain this model. But this is not really the case now what we know from our observations. So I will show you, for example, this is the one source which I was talking about, V8991. So this is the source which we monitor, okay, using Indian observational facilities. These red points are the recent points. So for example, this star was in quiescence phase, which went to the outburst phase around this time scale. Okay, there was a outburst here. Then again it came to the quiescence phase, and then within a short time scale, it again went to the outburst phase, and right now it is in the outburst phase. So this is the history of this source. And similarly, of course, this is the first time we have actually monitored this source both photometrically and spectroscopically around these regions when it goes from transition phase. So it's very important to have this spectroscopic observations because they give direct evidence of accretion rates. Okay, so if you have that kind of information during your transition stage, you can actually constrain much better the nature of the object. Similarly, in case of other object, D1647 array, we have monitored, this is the early epoch using Palomar plates, but then later on we find that this is in quiescent phase, went to outburst phase, again came to quiescent phase in a very short time scale, and again now it is in outburst phase. So what you see immediately is here that in general the quiescent phase are shorter than the outburst phase, which is opposite to the instabilities model which we know. Okay, so what does it mean is that our outburst periods are less than quiescent period. So you cannot actually explain these kind of accretion by just depleting the grain, disk. Okay, you need actually some other kind of instabilities model. Okay, and this short quiescence is not enough to refill the disk within this short time scale. You need large time to refill the disk. Then you can have instabilities where they can produce further outbursts. So this is the qualitative statement, but we did a lot of quantitative estimate and we tried to calculate these alpha parameters, and we found that all these alpha parameters are inconsistent with what we know from simple instabilities model like Bell and Hill models. Okay, and also in these instabilities model, what people have assumed is that accretion rate is constant. But what we found later on, I will show you that generally accretion rate is not constant throughout the lifetime of these episodic accretion events. And even if you change the accretion rate, mass outflow rate, you can find unrealistic values for this kind of alpha parameter. So it's very clear that you cannot explain this kind of model by simple model. So what could be the reason for these kind of outbursts? So what we found is that probably there is some kind of outflows happening these kind of events. Okay, so one thing we know that when accretion is happening, you also see the outflow is happening. Okay, that is what correlation I was talking about. But what you see that, so this is the first outburst. So basically, how you calculate the outflow? So outflows in young stars, basically you calculate through the blue absorption through. Okay, this is called PCV profile. Okay, so for example, this is one of the line. For example, this is one of the recombination microhydrogen HL5. And if there is a wind or some matter is thrown away, you see the outflow here. So this blue part of this, basically the energy or strength of this line can give you the outflow velocity or wind velocity. So what you see when there is an outburst, you see strong wind velocities, and then with quiescence you see no wind velocity. That is understood. Okay, but you just before quiescence you see there is a strong kind of outflows which are happening. Okay, so there is a hint of such kind of intermediate or pre-quiescence outflows in these kind of sources, which can actually produce such kind of instabilities which cannot be explained by these kind of events. Okay, and we have actually studied these objects in detail, and we found that probably this is one of the reasons why these kind of time scales are shorter, like quiescence time scales are shorter than the outflow time scale. And also many other lines in spectroscopy, for example, like oxygen line, which is basically indicator of turbulence, okay, also give indication that you need such kind of intermediate kinds of events like turbulence or pre-quiescence kind of outflows to explain these kind of stabilities. So we try to understand how we can actually explain these kind of observations. So there are a lot of simulations which are available in the literature. Basically depends on the magnetic field effects, on the magnetoscopic disk around the star, and we have found that if we use these kind of models where magnetic field is an important parameter, they can actually cause the accretion without depleting this. Okay, and then these can actually resume again this kind of normal kind of accretion. Okay, for example, you can see cartoon here. If you don't have such kind of instabilities, you see stable kind of this magnetic rotation disk here. But when you have an outburst, you see these funnels are opened up, so you don't need to actually fill up your disk or drain your disk during this accretion and outflow phenomena. So probably this is one of the instabilities model which can explain such kind of sources. Okay, so this is something new research. Okay, so let me now go to the outflow and accretion relationship. So as I said, these outflows are the most efficient way to take away angular momentum from the star disk system, and they prevent the star from spinning up. So it's very important to understand this argument. So if angular momentum resolved by the outflow is angular momentum transferred from the accretion, so then what you expect that this outflow is proportional to accretion, which I already showed you in some of the line profiles. Okay, so again, these kind of sources are very important sources to understand these kind of relations. Okay, so for example, I can just show you how first time we have seen observationally these relations. So for example, if you see this is the accretion rate and this is the time scale. So when star is at quiescence phase, which you can see this line profile, and you don't see any wave profile here, outflow profile here. Okay, and when the star is at outburst phase, you see this absorption tube, which indicates the high velocity, wind velocity. So when accretion is high, you have these high wind velocities. When accretion is low, you don't have wind velocities. So you see this kind of correlation, accretion and outflow. Okay, but what you see that in case of a, for example, it doesn't happen always in the extreme condition. Even when star is even in between the heavy outflow or quiescent phase, you can see lot of kind of this wind velocities. Okay, so here what I plotted is basically the wind velocities calculated using line profile. So this blue shows blue shifted, which is the absorption profile, and the red one is the emission profile. So what you see is that intermediate also we see very high wind velocities. It's not always the case. So there is something in a short time scale. There is high outflow, okay, which cannot again explain by this model. So this we have also monitored, for example, high resolution meter, for example, this is HRS spectrogram, which is like 30,000. So what you see, this again is the absorption profile, which indicates the wind velocity. So you see the wind velocity goes from 400 to 700 per second, which actually cannot be explained by simple launching mechanism where you can actually have flows because of thermal stability or displacement. So you need some other kind of launching mechanism to explain very high velocity. Okay. So this is in this case. So we try to understand what possible mechanism for these kind of outbursts to explain. So we know there are very many mechanisms which are available in the literature. For example, simple is the disk wind because of the flares which are released in the disk, but in this case, these disk wind are not that these outflows are not very stable. Okay, although we have seen a very direct correlation between outflow and accretion, okay, for a larger time scale, but shorter time scale there are a lot of variations. So they are not really stable at shorter time scale. So typical velocities, what we need in such kind of event to understand should be like aquarium velocities, but we don't see these velocities. You need a very large accretions, so you cannot explain these by simple aquarium rotations. So this is not a very good example to explain these kind of outflow mechanism. The next one could be because stellar winds coming from the central stars. Okay, so these stellar winds are also what basically happens because of radiation given through these open field lines. Okay, again these stars, because it is going in the episodic accretions, is not very stable, so you don't see such kind of stable winds from the star. Okay, and these kind of star winds are not very large as compared to the disk winds, so they are limited by their terminal velocity. Okay, so what we see in our case is that we have a velocity which are going from -400 to 700 kilometers, much larger than the terminal velocities of these stars. So you cannot explain this by simple stellar waves. So what possible mechanism which has come out is basically magnetic pressure driven these kind of polar winds. Okay, so this can actually happen in polarized regions of the stars, and they have very small inclination angle like 10 degrees. So this is actually what we find from our observations, because we can actually calculate every inclinations, and of course we know the velocities. So since these kind of winds are going further away, so they are much unstable. Okay, and they have high velocities in polar direction because they can escape much further away, and of course it's small inclination angle. So this is one of the possible mechanism which we have come out. Okay, so this is just so explain what I talked about. What is the physical mechanism behind episodic accretion event? So disk instability models cannot explain the short period questions, okay, which we discovered in our observations. So what we need is the heavy magnetic activities in our data, which basically finding the instabilities in this magnetospheric accretion. So are outflows correlated with the accretions? So what we see long time scale, but not in short time scale. That's why we have to invoke new stabilities models. Okay, what are the driving mechanism of the outflows? So I think probably most important, which we know now, this kind of object is the first detection of magnetic driven polar winds. So this probably is the very important driving mechanism of this outflow. Okay, so just one slide, or a couple of slides. So what we need now future to understand this basically that how these things are happening within the snow line of these stars, where a lot of chemistry is happening. So actually we have already started to understand the chemistry of this, because they are very important to understand the planet formation. So this is one thing which I am looking forward to discuss with the expert here, that what kind of chemistry is happening and how this can affect the planet formation. And of course we will also study this from GMRTs and others. Thank you very much.
So we have time for a few questions. We have more time for discussion later. No more questions, please.
We are choosing two stars which are not surely the brightest ones. Yes?
So they are basically, when they go in the outburst, they are quite bright.
So it's 12, let me. That's what you have shown.
No, those are the classical ones I showed. So these ones, actually, yeah, there will be around small magnitude in these other bands.
Yeah, so are they, first of all, the brighter stars to increase this sample, to observe this with the smaller telescopes, which is much more easy to do on the small telescopes than on SOLT or something like that?
Yeah, so no, so what we did, we have actually observed this with the 2-meter class telescope in India. So all this photogrammetry and spectroscopy was done by Indian telescope, like 2-meter class telescope. And we then also we did spectroscopy using 2-meter Indian telescope. But then when we found the evidences of these instabilities and high velocity waves, then we approached to SOLT neon meter only for spectroscopy. So this high resolution spectroscopy was done with SOLT once we had some important results from the small telescope. So yeah, so actually smaller telescopes are very important to monitor these objects. That was the basically goal. And once we came to know something new happening, this very high velocity winds we have never seen in literature coming from this object, then we approached to SOLT.
Okay, and then the ultraviolet should be very important in this case. You may mention only the red telescopes which are working in the infrared or red part, but we have to look into ultraviolet, for example, Russian spectrum UV or UV UV. So this is a good implication. So it's very good to learn what will happen.
Yeah, so we will actually also, Professor Bose will talk tomorrow about UVIT, ultraviolet telescope. So we have proposals to monitor this from space.
Another, if you have spectral monitoring, you should know the inclination angle.
Exactly. So,
but you were speculating about this.
No,
but you should know.
Yeah, we know, but actually from spectroscopic signatures also we can spectroscopy of the central star. Then you have the clumps which are thrown away. So you can actually do the spectroscopy of those clumps, and based on the line profile, you can actually construct much better inclination angle. And inclination angle is very important to pinpoint the molecules. Otherwise, everything will be wrong.
Sure. Yaroslav.
You came to the conclusion that episodic is to the instabilities magnetic field around the crater, right? So what would be then the radius of the disk, of the inner disk, which is affected by this magnetic field? So what do you expect the radius would be?
So that is actually a few angstrom unit.
Astronomical?
No, sorry. This is something like, for example, if you see solar kind of star, it's like a 4 or 5 solar radius kind of thing. Okay. But then once the outburst is happening, it can actually push this radius much further away. So roughly we have found that from 6 solar radius up to 20 solar radius, depending on the nature of the sources.
And does it enough material around this 5 radiuses to have such a flash? Or
yes, so for example, if you see these polaroidal magnetic fields can happen only in the inner disk. Okay, so you need such kind of shorter radius.
Colleagues, I suggest to use the coffee break also for the discussion. We have 30 minutes coffee break. We have enough time. Very pleased to talk. Thank you very much. I also have some questions to you, but we could name at least a that's microphysics in visuals of
is there a point?
sometimes the picture of outbursts and also some kind of details and so on, they should be found in the observation by some non-uniformity in the dust and also by the research.
Объявление небольшое можно? Прошу всех докладчиков, сначала по-русски, потом стоять ну, рядом с доской, чтобы было видно на камеру.
Ну,
I asked two presenters stay near desk for streaming.
Translation for the institute,
For
for Russia,
all world, YouTube.
all the world. Okay, everywhere. They can follow us. Okay.
Well, first of all, I would like to thank the organizers for this wonderful meeting, and I want to apologize for changing the topic of my presentation. Today, I'm going to talk about dust microphysics in regions of ionized hydrogen. But first, some introduction into dust physics and our current state of knowledge about space dust. Originally, the models of space dust were based on absorption studies. They have been developed in the early 60s, actually. And there are two main ingredients for dust models, and what these ingredients come from absorption studies. The first ingredient is the so-called UV band, which is enhanced absorption in the ultraviolet band, specifically at the wavelength of 2175 angstrom, which is believed to belong to graphite material. And there are two other features which are called silicate features, and again they relate to enhanced absorption at around 10 and 18 micron. These two absorption features are believed to belong to silicate materials. And these two absorption features have given rise to the so-called graphite silicate model, which was very popular and actually is very popular now. Actually, these silicate features can be seen both in absorption and emission, depending on the dust ray temperature. When in the early 80s, infrared observations have started, which allowed to observe dust emission, not only absorption but emission, it became obvious that we need to add other components to graphite silicate models. And these two components are very small grains, which are heated stochastically by absorbed photons, and thus they can be heated up to much higher temperatures than big grains. And another component is now generally referred to as polycyclic aromatic hydrocarbons. And these particles, which are actually intermediate between big dust grains and large molecules, I believe to consist from some number of benzene rings. Probably in the interstellar medium, we do not have such regular structures like ones we have shown here, but definitely grain particles should have some aromatic component in them, because this aromatic component is responsible for infrared emission bands, which are observed in the near infrared wave range starting from about 3 micron and up to 20 micron. So now we have this is one of the popular dust models, which is in wide use now, which has been published by Akimkin V in 2001. And basically, it consists of particles of three sizes. Big grains, both graphite and silicate, with an average size of about 0.1 micron. Very small grains, only graphitic ones, with the size of about 50 angstroms, and pHs, polycyclic aromatic hydrocarbons, with the size of a few angstroms. Why we believe that there are no very small silicate grains? Because they are heated up to a high temperature, and if there were silicate grains in the interstellar medium, we would observe 10 and 18 micron features in emission, which we don't. So very small silicate grains are not very abundant if they exist. As I said, this model is very popular, but this doesn't imply that it is correct. And actually, there are many studies which indicate that there are some other combinations of grain materials which are possible and which are able to
fulfill all the observational constraints. This is quite a sad situation because dust properties are very important. Dust is very interesting by itself as a raw material for planet formation, for organic material evolution in the universe. And dust is very important because it is an obstacle for many other observations, including cosmological observations. And we need to know dust properties in order to get rid of this obstacle in a correct way. And at the same time, the ultimate dust model is still late. We still do not know for sure what dust properties are. And actually, there may not exist an ultimate dust model at all because we have numerous indications that dust properties differ in various regions of our galaxy and other galaxies. So actually, in order to understand what goes on with the space dust, we need to understand the evolution of dust grains. And to study something, we usually have to destroy it. So if we want to find out what dust properties are, we need to look into regions where dust grains are destroyed, and then we will see what are these destruction products we may infer dust properties. And the promising regions for dust destructions are star-forming regions, specifically H2 regions, which surround hot young massive stars. There are several dust destruction mechanisms which operate in various environments. These mechanisms are basically referred to as sputtering. This is dust destruction due to grain-gas collisions. Shattering, which is dust destruction mechanism related to grain-grain collisions. And two mechanisms which are related to dust temperature, dust thermal evaporation, and dust destruction due to absorption of local heating of the dust grain. And all these mechanisms are operating in star-forming regions. The main source of information about dust grains are now these two nice instruments. Spitzer mostly provides information in the near infrared band, while Herschel is a source of information at a longer wavelength. And it is basically assumed that this emission mostly comes from aromatic particles. Intermediate infrared range, which is represented by 24 micron Spitzer band, is produced by very small grains, statistically heated very small grains. And emission at longer wavelength belongs to big grains with a size of about 1/10 of a micron. But actually, this interpretation may not be that straightforward, and some emission at 24 micron may also come from hot big grains as well, not only from very small grains. Well, these are infrared bands from Spitzer and Herschel, and far infrared bands from Herschel from the Spire instrument are shown here. We have first encountered the problem of dust evolution when we studied dust emission from extragalactic star-forming region. It was noticed quite a long time ago, back in mid-2000, that infrared emission from polycyclic aromatic hydrocarbons is much weaker in galaxies of low metallicity than in galaxies of high metallicity. This is the original plot from Engelbart et al. 2005 paper. Here, the ratio of fluxes is shown at 8 micron and 24 micron, which is believed to represent a fraction of pH in the overall dust mass. And this is the galaxy metallicity. And one can see that this ratio, 8 to 24 micron ratio, is about 1 to 2 in high metallicity environments, and it is lower than 1/10 than in low metallicity environments. Here the same correlation is shown in terms of, again, metallicity and the so-called QPH value, which is a percentage of pH mass in the overall dust mass. And again, we see that in galaxies of solar metallicity, this fraction is about 4%, and in galaxies of low metallicity, this fraction is only about 1%. or less. I want to stress that this is a relative measure of pH abundance. So for some reason at low metallicities, less carbon atoms are incorporated into pH particles. This is how infrared spectra look for various galaxies. This is a low metallicity galaxy compared to, and there are no aromatic features at all. And these are high metallicity galaxies where we see a lot of aromatic emission bands. We started from studying the Holmberg 2 galaxy, which is shown in this nice picture from the Hubble Space Telescope. This is a low metallicity galaxy, and we wanted to find a proof that at low metallicities, destruction mechanisms are more effective than in galaxies of high metallicity. So we have started from the galaxy with very low metallicity, where this should be pronounced to the highest degree. But the actual situation turned out to be more complicated. As I have shown here, there are no aromatic features in the overall galaxy spectrum, but there are some regions which are bright at 8 micron, at 24 micron in this galaxy. We have obtained spectroscopy for these regions. We have determined the metallicities, their ages by equivalent width of H beta line. And we have found that while 8 micron flux decreases with age, and 24 micron flux decreases with age, their ratio actually grows with time, as if pH contribution becomes stronger with time. This is something that we didn't expect. We expected this correlation to have the opposite sign. Then we have compiled more information about 8 other galaxies, including our own observations at the Specialist Physical Observatory at the 6-meter telescope. And we have compiled data on metallicities, ages, infrared fluxes for about 100 star-forming regions in 9 galaxies. And we have found that in low metallicity galaxies, not only in Holmberg 2, but in other galaxies as well, the fractional mass of pHs grows with time in star-forming regions. These are low metallicities galaxies. Then intermediate metallicity galaxies do not show any correlation between pH fraction and age. And the expected correlation, which would reflect the destruction of pHs, is only seen in high metallicity galaxies like our own. And we have proposed that this can be related actually related to dust destruction, but not to pH destruction, but to destruction of larger particles. And pHs which appear in star-forming regions are actually fragments of larger particles. And there is actually a new dust model which allows to account for this process. This model has been published in 2013 by Anthony Jones et al. And the novel feature of this model is that it contains carbonaceous particles of 2 kinds, aliphatic and aromatic, and it allows to make a transition from one type to another, and thus to try to account for observed variations in carbonaceous particle models. This is the overall picture of dust evolution in the interstellar medium according to this model. So first, aliphatic particles are produced by intermediate mass stars. Then this particle travel through the interstellar medium. They are becoming aromatic under the action of the interstellar ultraviolet radiation. And then when they happen to be near the massive hot stars, they are destroyed, and we see their fragments as a source of aromatic features in the star-forming region. And this is where dust microphysics comes into play. So when you want to account for dust evolution in the general interstellar medium and the star-forming region, it is not enough to take into account the grain size distribution only. You need to take into account changes in the grain structure, which can be related to aliphatic versus aromatic grains, hydrogenated versus dehydrogenated grains in the case of carbonation grains, amorphous versus crystal and silicate grains, and so on. And you need to take into account grain charge. Specifically, in the case of pHs, you need to know whether your particles are neutral or ionized because they have different spectra. This is the predicted absorption cross sections for aliphatic and aromatic grains from Jones et al. Model. Red corresponds to aliphatic, purple corresponds to aromatic, and you see that the expected appearance of the spectrum is different for these two kinds of grains. So if you have a good spectroscopy, you can actually distinguish between the two. This is the expanded view of two regions at around 3.4 microns, at around 7 microns. There are strong aliphatic bands at 3.4 microns, and there is the aromatic band at 3.3 microns. So you can distinguish between these two kinds of particles in observations. You can also distinguish ionized and neutral pHs. There is a strong emission band of 3.3 micron for neutral pHs, and it is nearly absent in the ionized pHs. And unlike neutral pHs, ionized particles have very strong emission around 8 microns, which is nearly absent in this case, and 11 micron emission is stronger in neutral pHs, and so on. Again, this can be seen in observations. Is it actually seen? To check this, we actually may observe H2 regions which are close to the sun, which can be observed with much detail. There are several types of H2 regions, and the closest to the sun is the blister H2 region, the famous Orion Nebula, which is actually a region of hot gas on the surface of a giant molecular cloud, Orion A. This is how it is absorbed on a large scale. This is this image with the Hubble Space Telescope. And there are several features of this nebula which are seen in this picture. And most interesting from the point of view of dust observations is this bright region which is called Orion bar. It is now assumed that the ionization in this region is produced by the trapesium cluster, which consists of very bright young stars, and the brightest one is this Theta 1c star, and this underlying region is ionized by this star. And actually, the Orion bar is also the border of this ionized region. This is the attempt to present M42, the Orion Nebula, as it would have been seen from the side. This is the surface of Orion A molecular cloud. We are looking from this direction. There is main ionization front on the surface of the cloud, and then the material bends somewhat in our direction. So there is a wall here, and it is also ionized, and we look at it from this direction. So this is the ionization front seen from the edge. So if we look across this region, we can see dust properties in the neutral material and in the ionized material. Let's see this site. Orion bar has been a subject for many observations in the infrared bands, and one of the first attempts had been published in 1994 by Ojha D.K. This is the cut through the Orion bar of the 3.3 aromatic micron feature. And you can see that the intensity of this feature slowly grows as we go in this direction. And then there is a sharp drop of the emission at this band as we go from neutral material into ionized material. And this drop has been interpreted as an evidence of very effective pH destruction in the ionized material. But the real situation may be a bit more complicated because 3.3 micron feature is just one feature, and it belongs to neutral pHs, and the situation can be more complicated if we want to see ionized pHs as well. This is another example of observations of Orion bar along this cut, and here the authors of this paper showed that the ionization degree actually grows as is expected as we go from the neutral region of Orion bar to the ionized region. I don't understand why they have ionization degree of 120% on this plot. There is no installation in the paper. Yet another example showing that pH's properties change across the Orion bar. These are spectrum. This is the distance from the θ1c star, and we see emission of ionized neon from the ionized region, and it drops as we go into the Orion bar, and then simultaneously intensity of aromatic features grows. But only 7.7 feature goes to 0 in the ionized region. There is emission of another aromatic bands well into the ionized gas. And this is actually seen in other ionized regions as well, specifically in this IC434 region, which is produced by Sigma Orionis star. In this paper, observations were presented of this part of the famous Force-Fed nebula. And you can see that there is an ionized region marked by H alpha emission, ionized neon emission. And in this part of the nebula, the main of the course, we see aromatic emission, aromatic infrared band at 11.3 microns. But while the maximum aromatic emission comes from the main, from this edge of the nebula, we still see some aromatic features in H2 regions as well. So pHs are not actually disappear as we go into the ionized region. They still exist at some distance from the ionization front. And this again can be an indication that they are not only destroyed in the ionized region, but are also reduced due to destruction of larger grains. Well, there are some estimates of the lifetime particles in the Force-Fed H2 region. It is about 5,000 years in Orion bar. The lifetime is somewhat smaller, less than 1,000 a year, because the distance from ionized star is much greater in this case than in the Orion nebula. Well, I will only skip this part and say some final words about a bit more complicated situation. This situation was first noticed by Oxendorf et al. In 2015. Again, this is this Sigma Orionis star, which ionizes the surface of Orion B, giant molecular cloud. What they have noticed that there is an excess 24 micron emission around this star. This is an image composed of 8 micron emission shown in green and 22 micron shown in red. There is a clear excess of 22 micron. The model of the dust wave. According to this model, there is a flow, photon evaporation flow of the surface of Orion B cloud, and photon evaporating material, including gas and dust particles, flows in this direction. But when it approaches Sigma Orionis star, the radiation pressure from the star stops dust grains, and they form an arc-like structure around the star. And they have interpreted it as a dust wave appearing because of radiation pressure around the star. They have also applied this model to other objects as well, in particular to the famous RCW120 object, where they believe similar arc-like structure is observed, and they also describe it to the dust wave. And this is their latest work published last year, Oxendorf and Tillens, where they claim that there are actually two arc-like structures in the Orion region around Sigma Orionis star. One of the structures is the 24 micron structure,
which surround the star at a distance of about 1/10 of a parsec. And then they claim that there is another arc much farther away, at a distance of about 1 parsec from the star. And they claim that the dust material in the Orion B cloud consists of 2 dust populations. One dust populations is represented by compact grains, which experience less gas drag, and so they are able to move further to the star. And these compact grains are heated to 75 K, and they are source of the emission of 24 micron at this small arc. And there is another population of dust which consists of fluffy grains with a large cross section. And these fluffy grains form this extended arc. They are far away from the star, so they are heated only up to 24 K. And this is why they are absorbed at 160 micron. Why same particles are absorbed at 8 micron as well? This is a question, and the paper by Oxendorf and Tillins doesn't provide any answer. But I will skip these figures. They simply state that according to Herschel observations, dust present within Orion Nebula, and it is heated up to quite high temperature. And the final remark is about silicate grains, which are also present in the Orion Nebula. They are heated up to high temperatures, and there are signatures that some of these grains have crystalline structure. And the fraction of crystalline grains is much higher than in the general interstellar medium. So this is another example of restructuring dust grains in H2 regions. And I will stop here.
Okay. So, question please. Yes, sure.
So this pH destruction you showed in 2 samples, one in external galaxies and one in Milky Way. So how this does to microphysics? I mean, one in large scale, one in smaller scale. So this morphology physics is almost same, or how do you explain that?
When we observe star-forming regions in external galaxies, we deal with huge spatial scales, like hundreds of parsecs, 2 to 500 parsecs. And in this case, like the Orion Nebula, other local regions, we are talking about scales of about 1 to 2 parsecs. And what we see on a large scale is simply some general indication that aromatic particles are not depleted as effectively as we would expect. Either they are destroyed less effectively, or maybe there is a source of this particle. And studying local H2 regions, we may actually see this happening, not just infer, but see.
Yes, please.
This aromatic gains, how do they have different?
Say it again, please.
You talk about like this aromatic grains and aromatic grains. How do they have different? What is this?
What is the reason? The origin may be aromatic, they are produced on the surface of grains, refining maybe not. I just try to.
Well, this is the question. This is a question we actually now trying to answer, and I forgot to mention that we are now we are developing a model which would allow to reproduce both aliphatic grains, aromatic grains, their mutual transitions, changes in the dust, in the size distribution, and with this model we will try to answer these questions about.
No condition. Okay.
This is not please.
So the equilibrium grain charge being included in modeling of this AHS, because depending on radiation environment, equilibrium charge
will be. In the current version of the model, it is not included, but I hope that
We have special talk.
in the next talk we will answer some of these questions.
In these detailed dust models, you did mention laboratory studies. Do you need this? Is this important?
Sure.
It is not mentioned.
Well, this is a description of our model. We do not do
Is
any.
it a detailed dust model?
Yes.
Yes.
What we need for detail. Well,
We do need laboratory studies, but we do not perform them ourselves.
My questions, one that's maybe the questions of tone. You have demonstrated the U graph on the absorbance of neutral and charged PAH. Could you please come back to this slide? Yeah, exactly. What means absorbance here? Yes. Some special term.
Well, these are not astronomical units. These are auditory units. So this is a cross section, absorption cross section in some units, normalized units.
It's just a cross section
Yes.
to radiation. Okay.
Normalized.
So, if no questions, thank you very much for this interesting. Now we have a coffee break. Yes.
У меня есть одна знакомая бабка, которая говорит, что может учить типа гору по крупным контактам.
Okay. Shall we continue the session? So we are moving to the next talk. Please, Vitaly Akimkin V. Please, the name is Vitaly. Легенда Виталий Борис Акимkin.
In this talk, I will discuss dark charging and some applications for two very different astrophysical environments. For dark, called conditions of protoplanetary and warm ionized conditions in H2 regions around young stars. So, dust charge has some fundamental properties of dust grain, and it can alter the dust microphysics qualitatively and in some cases dramatically. That alters dust and gas maximum interaction and dust interaction. So as these meetings together experts from different fields, I will start with just a couple of slides with some history. This is probably the first paper about dust charge in astrophysics. So this paper is in German. And Jung in 1937 considered dust charging due to two primary mechanisms collection of electrons and ions, free electrons and ions. Yeah, and Jung came to the conclusion that in general interstellar medium, dust grain is charged positively. That could prevent dust growth during the accretion phase. 1 year later, Axel Corbin considered a very smart mechanism to charge grains of different sizes to different signs. So this charging is due to interaction with secondary electrons, cosmic ray secondary electrons, and Corbin considered this charging as a mechanism to increase dust growth in protoplanetary disk-like conditions. Several years later, Spitzer published his fundamental paper on dust charging, and he came actually to the opposite conclusion that dust grain in interstellar medium should be negatively charged. So the answer probably is somewhere between, because it just depends on the condition and the balance between two primary mechanisms, photoelectric charging and plasma charging. After that paper, there were just a lot of papers on dust charging, and I would just highlight one of these papers. Haran and Goretz considered another charging mechanism, charging due to secondary electron emissions. When an electron is energetic enough, it could provide not a negative charged current, but otherwise positively charged current. And the second feature of this paper that they considered not as equilibrium solution for dust charging, but fluctuating plasma temperature. And they found that there are two stable solutions actually when you consider secondary electron emission, positive one and negative one. And this also could lead to the rapid dust accumulation. So on this slide, I summarized the main mechanism of dust charging. So the first one, the most which works in the most conditions in photoplanetary in interstellar medium is photoelectric emission and plasma charging. So I would highlight the last two mechanisms, triboelectric charging and active emission. They are believed to be responsible for the formation of the volcano lightning. This triboelectric charging is the, so we know this charging for this mechanism for I don't know, several thousand years, but
Yes.
yeah, exactly. Yeah, but I just saw a cat. But actually we don't understand fully the exact mechanism, and I just want to show you two experiments on this triboelectric charging. These authors just took a Mars soil simulate and shake it in a box, and then separate dust grains by applying electric field into two separate populations of negatively charged grains and positively charged grains, and they found that the larger grains are predominantly positively charged than the small grains. The another experiment was an experiment where silicate dust grain, micrometer size, was collided with a silicon substrate. The grain was neutral before the collision, and it was charged due to this triboelectric charging after the collision, and then eventually stick to the substrate because substrate and dust grain had different charges. So dust charge is very difficult to observe, almost impossible, but there are phenomena that could be attributed to the effect of dust charging. One of these phenomena is so-called lunar horizon glow. Astronauts during the Apollo 17 mission, when they orbited around the moon, their were prepared just before the orbital sunrise. They were prepared to observe zodiacal light, but they did observe zodiacal light, but it had a strange companion, unexpected lunar horizon glow. So this one is zodiacal light, but there were just thin emission due to light scattered by dust grains above the lunar surface. One of explanation of these dust grains is that these dust grains are levitating above the surface, electrostatically levitating. Another example is so-called spokes in Saturn rings. They were observed by these missions, and the spokes are bright in the forward scattering light and dark in back scattering light. And the origin of this is also dust levitating above certain rings, electrostatically levitating. So the last example from our solar system, here is the image of Hale-Bopp comet, when it was at this distance from the sun, and these authors tried to fit the shape of the tail, and they came to the conclusion that it's better to account Lorentz force to explain the shape of the tail. So probably the dust grains must be charged to just explain the tails of comets. So, and now I'm switching to the studies that we are working on. So there is a huge problem in the contemporary dust evolution models of protoplanetary disk, namely electrostatic barrier against dust growth. So the simple estimates of typical relative velocities and electrostatic energies of dust grains leads to that at some point, at some size, electrostatic energy just exceed the relative kinetic energy. So grains could not just stick to another, and the collision cross-section is almost zero. And this was done by Okuzumi, and 2 years later he published a paper where he showed that the size of this frozen zone, the zone where dust just stops and doesn't grow because of this strong electrostatic repulsion, is almost the size of the disk. So our goal is to switch these schematics into some numbers and to try to find the solutions of these problems. So we solved the Smolkovsky equation, the equation for dust tubulations, and added to this equation this term that considered the reduction or increase of grain-grain cross-section due to electrostatic interaction. We consider two charging mechanisms, photoelectric emission and plasma charging, and this mechanism leads to the following charging structure. So in the illuminated disk atmosphere, grains are positively charged. In the dark and dense midplane, grains are negatively charged. So you can guess that there is zero charge surface somewhere in between. And here, so in the densest parts of the disks, there is an important effect when the number density of electrons is comparable with the number density of grains. So every grain feels the dearth of free electrons, and their charge is reduced. So here you can see the grain charge state depending on the grain radius for two representative dust size distribution, so-called MARION distribution and Wolf-MARION distribution. The red line is the grain charge that would be explained the standard theory of dust charging in plasma, and the blue region is the grain charge that is calculated with account for these electron depletion effects.
So this is how grain charge affects the dust tabulation. The color depicts the mean grain size. So if we see some kind of red line that we are okay, so we can grow pebbles in the protoplanetary disk. But the blue color depicts that we are on the before the electrostatic barrier. So it's bad for the planet formation theory because you cannot grow microscopic bodies inside the disk. So you can see that dust grain could grow up to several microns in disk around disk midplane and on the zero charge surface. On this picture, the only considered relative source of the grain collisions is Brownian motion. But in case if the disk is turbulent, in that case grains have additional source of relative velocities, and you can see that the electrostatic barrier could be overcome. But this picture is only for compact grains. But we know, we believe that grains in protoplanetary disk grow as fractal aggregates. In that case, the turbulence is not so effective because in case of turbulence, you need the difference in aerodynamical cross sections relative to the grain mass. So in that case, the whole disk extent where we believe the dust grows, we don't see the efficient dust growth. So the only growth occurs on the dust zero surface, and as we can see now, one of the possible mechanisms is just the growth of dust grains on this surface and then returning dust grains into the disk midplane. And in the disk midplane, the big grains could grow further because of they are just behind the charging, behind the electrostatic barrier. And now I switch to another topic, to the grain charging into the in H2 regions. Here you can see the mean grain charge in an H2 region in completely different environments, depending on the distance from the center ionizing star. So you can see that most grains of different sizes are charged positively near the star due to photoelectric charging, and the charge decreases with distance due to decrease of the radiation flux, and then it jumps around the boundary of the H2 regions, and then it's again positively charged. So these charge gradients lead to interesting structures in the inside the H2 region. You can see that for some grain sizes, especially for graphite grains with several hundreds of angstroms of size, you can see the double peak morphology. So we are now trying to check whether this double peak morphology in dust density could produce this double peak morphology in 24 microns emission or other emission at 500 wavelength. So I came to my conclusions. So the first conclusion is on the protoplanetary disks. So currently, electrostatic barrier is very little studied problem of contemporary dust growth of plate formation theory, and it is still a problem. And the second conclusion is just dust charge should be considered in the H2 regions models, and it could produce these images, these double ring structures in H2 regions. So thank you.
Question, please. Okay. Yeah, please.
If we consider molecules, we have positive molecules, ions, and negative molecules, anions. Is it possible to assume that we have both charge positive and negative for dust? And what?
For dust grains, yes, the dust grains are both positive, could be positively charged,
simultaneously.
yes, and negatively charged. So
you can see here that actually the mean grain charge is 0, and you have just a Gaussian distribution around 0. And,
let me somewhat specify the question. You are talking about the mean charge, but I was asking that the molecule, polar molecule, has charge from one end positive, from other end negative. It is molecule, it's very tiny piece of matter. If you have some bigger piece, say D grain and so on, especially dielectric, you could easily have the charge positive on one end and negative for other end. So to say about the mean charge is a very big exaggeration, because in the microphysics you should take into account the relief of charge. It could be quite complex, and you could, for instance, avoid the sticking because of charge for the mean charge, but from the point of view relief, you could easily find that negative portion of one grain could be sticking to the positive. That's easy. The question was exactly what is that? What is your opinion about the reality of so-called mean charge for the dust grains?
So what I see in the astrophysics now is that it just inherits the very important, very basic results from the so-called elastic plasma physics. And I don't know if there is any, how to say, reliable results on the charging of these very irregular aggregates, because in that case, the typically used theory, the so-called orbital motion limited theory, is not applicable to the problem, and it's just hard to calculate the charging itself, and the interaction of dust grains with some charge on it, but is just distributed charge along the dust grain. It's too hard.
It's a matter of statistics and so on. That's the real life is much more complex than the model of uniform charge distribution. Okay, sorry for this, but I think that you should take into account this, at least in your talk, that the real life is more interesting, is more complex, and the idea of one charge for the grain is not correct, because you understand what they talk about.
So I would mention a very interesting experiment on the International Space Science, where they
Space station.
Yes,
sure.
Space station, and where they observed just tremendous increase in dust accumulation rates, up to 4 to 5 orders of magnitude in a sample of dust grains. And they attributed this tremendous increase to the dipole interactions.
Yeah, what we are talking about, yes, sure. Yeah.
You spend too little time, perhaps because of lack of time, on the H2 conclusion about the charge segregation and the morphology in the infrared. So I didn't see the physics connection between the morphology of charge versus the emission, but most of it is thermal emission. Now, charge, how is it affecting the emission?
Yes, so there will be talks by Maria and Yaroslav. They probably explain it more details, but shortly speaking, so the charge affects dust dynamics and dust interaction with plasma and dust dynamics through the H2 region during the expansion. So grains with large charges are more coupled to the gas, so they stay inside the region. But other grains which are less charged just expelled from the H2 regions, and you see this differentiation.
It's interesting also continuation. What is the influence of charge on the spectrum? Because for molecules, no, the same molecule charge or not charge, they have different spectrum. That's why here also.
When you say plasma, what what is the degree of ionization? What is plasma?
Plasma is a system where the Lie radius is smaller than the size of the system, your system. So it's basically determination of plasma. So speaking of protoplanetary, this ionization degree
10 to the minus 15 is also plasma in these terms. So we have to discuss this interesting topic. Sure, that's thanks one. Maria, Maria. Probably the most popular name in the Christian war, Maria.
I want to thank Dmitry, Wiebe, and Akimkin for very brief introduction to our studies of H2 regions. And I'm presenting a small talk about the numerical model which we use in our studies of massive stars. You know that massive stars play a very important role in the universe. They are source of UV radiation, they are source of heavy elements, they heat interstellar medium, and they change star formation process in their environment. But our knowledge about formation of massive star is far from completeness. We are studying we are studying early stages of massive star life. This stage is visible because massive stars create H2 regions around of them. In the beginning, size of H2 region is quite small, and it is depend on density of gas, and the very beginning of H2 regions is called ionization bounded H2 region. At some distance from the star, rate of ionization is the same as the rate of combination. But after some time, we go to further extension of photo-ionized gas, because pressure of hot ionized gas is higher than the pressure of cold external gas. This H2 region is called density-bounded H2 region. And I will speak about density-bounded H2 regions. Observers found several classes of H2 regions. They have different sizes and different densities. We are studying compact H2 regions and extended classical H2 regions. This is a scheme of H2 region. This is a star. Star is surrounded by hot ionized gas. And in a density-bounded H2 region, there is a shock wave. Shock wave go in the front of ionization front, and there is a layer of shocked molecular gas between hot H2 region and the cold environment. So we developed a chemical dynamical model for describing H2 regions. This model is based on Zeus code, but in 2 dimensions, but we use this code only in 1D. Typical size of our computational domain is from 3 to 15 parsecs. And we typically have from 500 to 1,000 computational cells. We added a lot of cooling and heating process in this dynamical model, and we added chemical process in this model, and we improved the physics of dust grain. We solved system of rate equation in the chemical part of the model. Here you see these equations. For every type of molecule or ion, we can solve this equation in pure the space chemistry, or we can add accretion and desorption to our equations. There are several parameters of our chemical model: gas temperature, gas number density, cosmic ray ionization rate, pHs, photodestruction rate. We set up initial abundances of species and set up some network for rate coefficients. We have a very reduced chemical network, this one, in our published papers. But we are improving this network, and we want to make it comparable with the network which is used in Cloud package. We are using Leiden database for cross-section of photoreactions, and we use Unized database for rate coefficients. A dust model in MARION was already described by Vitaly. I just want to add that we can use MRN or Wingard-Draven size distribution, and we also include transfer of momentum from dust to grains to gas. And then we solve chemical reactions in every cell. We have distribution of sizes of grains, and we use this simple formula to solve chemical equations. This is so we use some average size of dust grain. We solve simple radiation transfer equations to get a rate of photoreactions in every cell of our computational domain. We set up a spectrum from Coolidge Atlas and can calculate optical depth for various reactions. Our equation of space change time, then chemical composition change every cell. There are several heating and cooling processes. I think that will be most important thermal process in our model. Here I will show you how our results. This is the distance from star, parsecs. You see distribution of gas velocity, gas temperature, gas number density, and the dust temperature. We also get position of ionization front and the position of photodissociation front H2 of CO. We also can make position of evaporation fronts of molecules from dust grains. Here you see evaporation for CO from dust. We can also model water and the height. And of course, each moves changes time. Example is from this. We are going from compact H2 region to extended H2 region. One of the most successful implementation of MARION model is studying of dust physics and dust emission in the H2 regions. there are a lot of ring-like nebulas, which are called bubbles. These nebulas were discovered by Spitzer telescope. And they have very typical view in infrared. 8 micron emission is a ring of 8 micron emission, and you see emission at 24 micron inside of this ring. And we try to model such objects and to understand what is going on with dust in such regions. We made a catalog of ring-like H2 regions. Anastasia Topcheva will talk about it on Wednesday, and we will model some of these regions in the future. One of the most popular H2 regions now is LCW 120. It looks like a very nice ring nebula on the sky, and we started to study this object in details. We are trying to reproduce infrared intensity distributions in this object. Here we see emission at 8 micron, and we see radial cut. So we try to reproduce these radial cuts with the MARION model and with the radiation transfer code Natalie. And Yaroslav Pavlichenko will talk about it on Wednesday also. This is a picture from Vitaly Akimkin V. We are studying distribution of charged dust grains, and we are trying to reproduce morphology of infrared emission. And I think that this work is quite successful. And now, just for some announcement, we have started studies. We have started modeling of H2 regions from star formation complex S231, S235. This complex contains seven optically visible H2 regions, and we are trying to model them and to understand how they live close to each other. And Andrei Mikhailovich Sobolev will talk about star formation in this region tomorrow. I just show the beginning of calculations with MARION. You see the beginning of S235 expansion. For 2 moments of time, this is the just beginning, and this is the more extended phase. You see dust gas temperature, gas number density, velocity of gas, number density of dust. This is the chemical composition of the very beginning of S235, and we want to model a distribution of molecules which we can observe and which we have already in our observational data. But real size of S235 is about, real radius is about 2 parsecs, so we have a lot of time to calculate. And in the conclusion, I just want to invite observers to give us some interesting problems to solve with MARION. And we are open for collaboration. And thank you for your attention.
So for the next question, please. Okay, yes.
In your model, do you account for turbulence? No. This is a thermal. I mean that equation of state only is a thermal equation of state, yes? But it is interesting. It is interesting to incorporate sometimes microturbulence in the equation of state and to see what happens. In the same And the same mechanism as you account for temperature.
Another question for the equation of state, what about helium here? Helium exists, but it should
Yes, yes, I just multiplied everywhere number density
by
one.
helium abundance.
Yeah, yeah.
Because otherwise it's not simple here. Okay, is that right?
Yeah, so in your bubbles, electric bubbles, you are actually assuming a single ionizing source to explain the morphology and mechanical. How are you choosing the ionizing agent, ionizing source?
So I set up star as I mean, I use atlas of stellar models. Is it your question?
Yeah, no, what I'm saying is that most of the galactic bubbles, you don't know which is the ionizing source which can actually producing these bubbles. So are you assuming a single ionizing source or?
So we are modeling bubbles which are
okay, no.
where stars are unknown.
I noticed in your last slides when the y-axis has 20 orders of magnitude in the dynamic range. So I'm sure numerical computation has a lot of challenges in the sense of making sure that there will be some terms which are so much orders of magnitude larger. So the error propagation while solving those equations, there are some real technical issues. I mean, would you like to comment on any of them? What special things are needed to be achieving these results?
Okay, so I have to think about this.
Ну, что поняли, да? Он спрашивает вас на одном из последних слайдов, динамический диапазон, десятки порядков, и как обеспечить здесь, ну, без десятков нет, конечно.
Beyond that, 1 to 20 or 1 to 20 or next slide.
This one. Вот 20 порядков. Как тут обеспечить?
These are the abundances. They don't have any feedback on parameters.
This is not a computational result. A differential equation.
This is the result. These are abundances. This is the final result. One tiny increment.
The question is of the propagation of waves.
Yeah, there are no propagations. These are no operations.
It's very yes, tricky things.
I think chemical equations in their system is sure to solve those.
This is not an input parameter. This is output.
Let's keep this point in mind for next talk. Okay. So, Ash. Thank you. Okay, again, the next talk by Tamara. Tamara is famous most popular name in Georgia, but also in Russia. Tamara Molyarova. She works at the Institute of Astronomy, but also she is still a student of Moscow Physical Technology.
My talk is related to reliability or unreliability of molecular traces of protoplanetary disk masses. And I want to start from what protoplanetary disk is. At early stages of its evolution, young stars are surrounded by circumstellar disks that we call protoplanetary because we believe that these are the places where planets form. And so we have many observational data on them in different wavelengths. You can see that here, and as we believe that with the planets there, it would be nice to know some parameters of the disks, and it would be able to obtain parameters observations. And one parameter that is secret is the disk mass and how we can take observation. very common way to measure this mass is observing just, but here we talk about molecular lines. And for example, molecule, it has easily observed rotational lines, and it is coupled to gas, and that's why it is used to measure masses of molecular clouds. Here it has some problems because the radiation is optically thick, but it has isotopes that are less optically thick, they are thin, and this is not a problem for molecular clouds. So maybe we could be able to apply this technique to protoplanetary disks to obtain their masses and use observations that are available now. By the way, you know that for interstellar medium there exists the so-called X factor. It is the ratio between CO and molecular hydrogen abundances, and its value is about 10 to the minus 4. Yeah. And what about protoplanetary disks? As you know, ALMA is able to observe in molecules, and there are already observations that are specially resolved and that are good enough to apply to this method of measure. There are some works, for example, Astro that uses emission of CO and its isotopes to measure the masses of disks. But in protoplanetary disks, the physical conditions are very different from those in molecular clouds. Temperatures there are very low and densities are very high. In some regions of disks, CO molecule can freeze out onto death green surfaces. This way it comes from gas to ice, and it becomes non-observable. This is the way how CO can become invisible, and maybe if we do not take into account accurately the CO result, maybe we can get much lower mass estimates. To find out if it's true or not, we have created a model of protoplanetary disk. Firstly, talk about physical structure. These are some formulas that are used to set the physical structure of the disk. They were standard, and I want to say that there are only 4 parameters that we change from one disk to another. This is power law parameter gamma. This is the characteristic radius of the disk. We use tapered disk model. This is approximate distance from the star where disk starts to end, RC. And of course, one of the parameters is disk mass. And also to set thermal structure, we need some star parameters. And in formula you see there is stellar temperature and stellar radius. And also, it is not mentioned here, but we also need star mass. But in our model, we do not consider them independently. We only set stellar mass, and then using evolutionary tracks by Paraffetol, we calculate the temperature and radius using knowing only stellar mass. So this is physical structure. It is stable, and we do not change it during the calculation. And what calculation? What calculation do we proceed? There is an astrochemical model. This is called ANDAS, developed by Akimkin et al. We run chemical model on those physical structure that we have said. This program, ANDAS, it solves the system of chemical kinetics equations. Then initial abundances like this are set, they're standard too. And we use a chemical network called Alchemic, that is mentioned in this Wiebe work. And And this network includes, of course, the surface chemistry and processes of accretion and disruption, and to take into account self-result and the other mechanisms. Well, and we run it until the age of 1 million years, because during this time, steady state for most molecules is reached. Well, and what we get? This is one model with standard parameters, and in this plot you see relative CO abundance in the disk, radial and vertical distribution. And what is important about this graph? Upper part of plot shows CO abundance in gas, and bottom plot is CO ice on gas-grain surface. You see that CO is very abundant in the disk only until about 20 or 30 astronomical units. And further from the star, there is not much CO, but either there is not much CO ice. It just goes somewhere, and the next slide shows us where it has gone. CO is frozen out further than 20 astronomical units, and it turns into grains CO, into CO ice, and on that green surface, this CO ice turns into it reacts with hydroxyl and ice, and it turns into carbon dioxide. So this is where it is gone, but what is important is that if we plot radial distribution, we'll see that CO is abundant only till 20 astronomical units, but further its mass is not very high, and though this class still 100, even more astronomical units, CO is abundant only in the inner part of the disk. This is radial distribution of CO. This is CO mass at the distance of r divided by molecular hydrogen mass. And if we adopt interstellar meteor X factor, we would get this ratio equal to 14 times 10 to minus 4. But it is so only for, it is true only for the inner part of the disk. In the outer part of the disk, this ratio is much lower. So if we integrate this over the disk, we will get the total CO mass to total H to mass ratio 5 times lower than we would expect from interstellar medium. So that means that if we do not take into account CO without in protoplanetary disk, we would get a much lower mass of disk if we only rely on CO emission. So, and maybe this is the result, and maybe we should use just 5 times lower X factor to apply to protoplanetary disks in this situation. Let's look at the many models. We created a grid of models that includes 2 actually grids of models. The first is a grid with fixed parameters. Those 4 parameters ran in our model listed in the table, and their values too. And in the first set of models, we use every combination of these 4 parameters to show, to be able to fix one of them or 2 of them, and see how the result depends on them separately. And also we create a set of random models where each parameter is chosen randomly in the same orders to see the variety of results. Well, here are some kind of results. Well, this is the ratio between the total CO mass in the disk and the disk's mass itself. And we would expect it to be about 10 to minus 3 for interstellar medium. And what we see from this graph that it is first much lower, second it varies with the star mass. Here we have fixed 2 parameters, gamma and r are fixed, and we vary the star mass, and we see that results are different, but not very much different. The next plots are not so optimistic. Here we fixed star mass as it doesn't affect much. Star mass is fixed to be one star mass, and here plots for different gammas, and every line is for models with one radius. And here we can see that for different models we can obtain very different results. But what is important is that for some gamma, like low gamma as 0.5, the results strongly depend on the disk radius, and especially for low mass disks. And if gamma is high, the results are different too, but not that much. And what is important to us about these graphs, that if we know the certain parameters of the disk, if we know already gamma and RC, we really get this that we want. We get near constant line. That means that it is a kind of X factor multiplied by some value. So in this situation, we can use the CO to determine disk's mass, but by another X factor. But if we do not know radius and gamma, we get something like this. This is a set of random models, and each point is one model, and color indicates gamma parameter. The size of the point is proportional to disk's radius, and so here we see that if we do not know precisely some parameters of the disk, we can get a very wide variety of CO relative mass. So disks of one mass can have very different amount of CO inside, dependent on their other parameters. So that means that in general CO is not very good mass tracer, because it depends not only on the disk mass, but on other disk parameters. In this situation, it would be good to find some other molecule that can trace the disk's mass, that would have a really flat constant value and very thin line horizontal. It would be very good, but we still haven't found it. But here you see similar plots for different very abundant species. This is carbon monoxide, dioxide, and water, and H2+. And you see that CO is not really the best molecule for this purpose. Others are not very good too, but CO is not much better. So what conclusions can we make? First, CO result is a very important process, and if we want to determine the protoplanetary disk's mass, we need to accurately take into account this process. The ratio between CO abundance in gas and gas, it depends on the disk parameter strongly. And so molecule is not a good tracer of mass unless we know other disk parameters. So it's necessary to find some other molecule that will help us, that may be able to help us to determine disk's mass. Well, thank you for your attention.
Question, please, yes? Okay. Regarding the last, it is necessary to find another molecule. You were talking about low mass disks around low mass stars. So number of molecules which is detected there is not that huge. So it's quite easy to find as possible. But there's only not only good tracer, but also
it should be
detectable tracer.
Yeah, this is important. I just mentioned it because it was important. It is the work that has to be done. We're going to do that. That's why I mentioned it. But yes, you're right. It should be detectable, but we just didn't think about it.
Okay. Will you do that the day after tomorrow? So how much work is necessary?
We just need to think questions are made.
There is the, yes, a question from the...
There is one question from Antonio.
Okay.
Why atomic initial chemical composition has been used for modeling?
What?
Disk is final stage of protostellar evolution. It is reasonable to assume that the initial chemical composition is already molecular.
I think it doesn't affect the result much because even in the first years of evolution, the abundances change strongly, and after I guess after a year of chemical evolution, there are abundances are not like those shown in the slides. There are molecules, many of them. Maybe it measures, but I don't think that it affects strongly. But I don't know. Really, we can try another.
I agree with this. Yeah. You were referred as a master of chemistry. The molecules were included in the process of chemical calculation.
We actually have several initial conditions in the model included. So this one is just one of these initial conditions.
Molecular chemistry is included or not? Molecular chemistry. Yes, it is included in the evolution. Okay, thanks. Okay. More questions?
Yes. Maybe can you return to the
Поправочка еще пришла.
show the diagram radius 2K. Yes, this one. What does it mean, the negative values?
This ratio, this is your number density divided by molecular hydrogen number density, and of course CO is less than molecular hydrogen, that's why it's negative.
Okay.
Тут еще поправка от Антона. Yes, but the significant fraction of molecules can already been frozen out of the beginning.
Yeah, that's true. We didn't try that yet.
Not only frozen in, but also that's evaporated. And it depends on the position of the element of the disk where it is. It's not easy to say that all the molecules from scratch were frozen in molecule. Nevertheless, thank you very much for your questions. Thanks. Okay, I just announced tomorrow morning I will touch on this issue. Maybe it will be interesting for you. Let's follow. What is that? So-called axial molecular gas. Okay, thank you very much again. So we have the last game list of today.
Давайте, где ваша презентация? Вашу флешку забрать. Презентация, флешку забрать. Получится, можете без
Нет, там это диск этот, вот и бридж. Там нижний много такой.
Ниже, ставь.
Ниже. Там много.
Чуть положили бы все на рабочий стол, и проблем нет.
Мы просто не успели. Вон.
Sorry, this talk is a substitute of another talk of a person who couldn't come. But the topic is very different, and the time duration is probably longer. But if you will interrupt me.
No, you have 20 minutes, that's all.
Okay.
Repeat questions.
Oh, good. Okay. When the time starts?
Very big presentation. Nice color.
Фронту ни при чем, он заберут. Как раз посещающий. So observations of masons in star-forming regions with ultra-high angular resolution. In case of Radioastronomy, I'm presenting this talk on behalf of me and the Radioastronomy Mason team mainly, Alakos and Hiroshi Imai. Oh, it doesn't work. Okay, that's the team. Next. Next. Turn in the chat. Chat. Okay, so it's a team. These are people who took part. So maser is a phenomenon of microwave amplification by stimulated emission of radiation. In this case, if we have amazing material, so it exaggerates or amplifies the ground instead of obscuring it. And the most recent survey is in Gray 2012, but there are a lot of things which are going on. So masers are observed in the molecular transitions of many molecules. They are shown here. Then maser images contain very tiny spots of very small sizes. And so one of the best resolutions which was provided before was VLBA, and it provided resolutions of a kind of micro-arc seconds. And this was very good, very great, and the size of the instrument is comparable to the size of our Earth. But now we have the instrument, which is the biggest instrument which was created by the mankind. It has sizes of 26.5 Earth diameters. And this is Radioastronomy, which was launched in 2011. So it can observe these masers, OH and water masers. Okay, so one of the basic innovations of Radioastronomy is possibility to observe water masers. So because these masers are the strongest, the sources contain numerous brightest and unresolved spots, and rather bright masers reside in external galaxies. So sensitivity is because it's only 10-meter antenna, only 10-meter antenna in space. But if you use it in combination with a big antenna on the ground, like GPT, you can achieve sensitivity of 3-4 Janskis for water masers and about the same sensitivity for hydroxyl masers. So angular resolution, which we can really achieve and actually check whether it is possible, not really map the source, but achieve this resolution in 7 microarc second, not milliarc second, but microarc second. So at the distance 1 kiloparsec, it will be 1/1000th of AU. That's a great resolution. And if we are talking about external galaxies, it will be something like 70 AU or at the distance of 10 megaparsec. So, water masers in the galaxy. Why do we know that the masers do exist even from the single dish? Because they display very high brightness. This is shown by the interferometry. The brightness in some sources exists 10 to the 17th K. So narrow lines, so the narrowest line which was detected in our observations is 0.03 kilometers per second. So it contains a lot of components, and polarization can be up to 100%. And it displays variability, sometimes on the timescales of hours, sometimes on the timescales of years. So these masers reside in the circumstellar disks and the outflows, so very important objects. So, and even one single line, water line, can be used for diagnostics, and it's written how many parameters we can draw conclusions about if we use monitoring. But in fact, also very attractive possibility is that since the masers are very small, we can try to measure parallaxes, trigonometric parallaxes, and measure distances to the sources, not in parallels, but in the diameters of the Earth orbit. So and this is a special instrument which works for water masers. And this is the first observations of this thing. Okay, and the distance which was determined is about slightly bigger than 5 kiloparsec, and the source was put in the outer arm, outer galactic arm. It's a great achievement, but in fact, if you know that the maser spots are very often have very complicated structure, they sometimes banded and so on at the different velocities or different frequencies. So this can play some tricks. One of these tricks shows us that, for example, the previous sources, they detected that the peculiar velocity is very small. If you look at the combination of all spots, we derive much bigger value of peculiar velocity. And further, if you have to pay attention to the form or to the shape of the maser spot, if the shape is properly chosen and you will derive the distance, this distance will be not 5 but 4 kiloparsec. And this source will be not in the forearm, but in between of the arms. And this is one of the major conclusions of star formation in our galaxy. This is one of our interesting achievements. In fact, what we have done, we have shown that for example, water masers, it's a tricky business. You should pay a lot of attention of what you're working at. But the method of masers for determination of the parallaxes is much better. It is shown in this paper. And so these parallaxes are used, are measured using VLBA. And if you compare the results which you obtain with water and methanol, this will give you a real conclusion. You should be very careful about this. But anyhow, so now we know the structure of our galaxy with much better precision. We know the rotation curve and other things with much better precision than it was known before for this part of the galaxy. So observations of minor sources in the galaxy with high angular resolution allow to obtain a lot of things. They are written here, but I don't have enough time. So do we need such instrument? Can we make it? Do we want to make it more precise? My answer, at least, is yes. But can we really make a step from millisecond to microsecond studies using space VLBI? One of the things is that if we increase the baseline, the sources tend to disappear. This is called they are resolved out. One of the reasons of this is a beaming. So the maser emission beam. And if we put antenna very far from each other, one of them come out of the beam. You don't see anything. Don't detect fringes. Another thing is very important is that the maser image contains halos. It is shown here. We see the central part and the halo. This is compact part. This is halo. This halos come out of something, for example, scattering. It appears very odd and chaotic. We don't know this sometimes, but they can be like seconds. While we need integration times of 10 minutes, if we want to detect something. But at the same time, there are other fields which shows this halos can from scattering. It can come from intrinsic properties, turbulence, and in this case, detect ultrafine features. And what do we need to know? So the same turbulence says there can be diffracted things, very tiny things which you can detect with ultra high resolution. and this is supported by model. So this Radioastronomy project, which was launched soon, and we made observations, and so these numbers were detected, and the best resolution which was obtained is this is mean they are milliards. This is like 20 micro arc seconds. This is proper. This is 20 micro arc second, but it is achieved, and this is real resolution. Yeah, this is not something like this is real one, not model one. And one of the things, best studied sources at present is if you say it was detected, for example, in 3.5 Earth images, and this is a signal. And if you see, this is a vector average spectrum, and this is a phase. And you see here that the phase which corresponds to this feature is not chaotic, it is not noise, it is arranged. And the other feature is also have arranged phase, and they're different. That says that there are two features, in fact, not one, but two features which are distinct from each other, and they really do exist. So in this case, we can make a model, and we see that the source, in fact, contains a bigger halo and two tiny spots and something like this. So this is a model resolution. This is 10 microsecond, but it is model resolution. But it corresponds to the sun, to the size of the sun, at the distance of 700 parsec. So this is the resolution which we have. So this is a great achievement. And unfortunately, we cannot determine the exact or absolute position of it, but we know the velocity. And these sources don't have these velocities. They have been only in special location. In this case, it's the center of the disk. This is the outflow, and we see this component here close to the center of the disk. This is very important. And here we see the outflow in continuum. And this feature, in fact, that's this feature, and you see that it is very highly variable. So it lasts, it takes place for 1 month or only a few months. Another feature which was detected in the same experiment also belongs to the center of the disk. This is the outflow. This is much huge disk around ionized star. So what do we have? I already told you about this. And how can we explain this? There are several explanations. I don't want to go into speculations. One of the things is just this can be turbulence in the center of the disk. When you see that yeah, I see this quite well. So if we approach in center of some structure, and we see that it's a huge difference in velocities, and we normally say, oh, it's a kind of Keplerian rotation disk. But the turbulent eddy has even stronger dependence. So if you approaching the center of the turbulent eddy, the difference in velocities becomes even greater. So this can be one of the things that, so with the Radioastronomy, maybe for the first time, we approach the resolution which allows us to see turbulent eddies and to see how the angular momentum is transferred into this or something like this. Okay. So there are several regions in external galaxies. Some of them, this is Large Magellanic Cloud, and some of them are quite bright. For example, this one in N113, it has a brightness of 50 and 70 Janskis, and it could readily be detected with the Radioastronomy. But unfortunately, there are technical problems or something like this, but we didn't detect. But we managed to detect the emission of fringes with Radioastronomy, with the Radioastronomy GBT for another, but it is extragalactic. This is at the distance of 16 or 20 megaparsec. That's far away. At 2.3 Earth images. So in fact, we are detecting star-forming regions in very distant external galaxies. But if we are talking about masons in the galaxies, this is our prize. The base is 19.5 Earth images. So actual resolution is around 10 or 11 microsecond. This is real resolution. That's 770 AU. So in fact, this resolution allows us to measure the parallax of the source in the large Magellanic Cloud. So we already have shown that this is possible in principle. So we have paved the way for determination of the distances to extragalactic sources in diameters of the Earth orbit, not in parallax. Okay, so this is shows the space baseline. This is ground baselines. Of course, if we would have two sources, two satellites, we would determine their size and so on. The summary of detections is something like this. So if you ask me the question, I will answer them and tell you what my conclusions are. Thank you.
That question, please.
So, the increase of resolution means that there should be increasing intensity, right, to detect this source. For example, you mentioned the intensity about 10 to the 17.
It's so not intensity. It's brightest temperature.
Brightest temperature in terms of intensity, in terms of temperature. So the question: are there any theoretical limits for
yes.
such
I know.
Even higher temperatures?
I will tell you that, for example, this emission is produced in molecular transitions. Yes,
right.
This is radiation. Radiation contains electric field. So this electric field can simply dissociate the molecule if it is too high. So there is some theoretical limit, but dissociation of the molecule, it requires input of energy. Yes, but the masers are beamed. So in fact, this limit is not well established because we don't know how the radiation which goes in one direction influences or dissociates the molecules. This is not studied at all. So we can speculate something, but there are no real physical measurements because in the lab we can never create dead beam radiation.
More questions? Okay.
This is a really impressive number resolution, but what is the lowest observable resolution with radioastronomy?
Lowest with radioastronomy?
Yes.
It is 10 meter antenna. Just calculate it by yourself.
No. In terms of informatic measurements.
Yes, that's it. That's the same. Because the lowest resolution, if you just
interferometric mode.
What? Interferometric mode, yes. Just we have baseline is one thing. Another is projected baseline. If you're looking at the source, which puts you the ground-based antenna and space antenna in the same direction, this is the lowest resolution. This is 10-meter telescope.
Which is the lowest baseline?
Yeah, that's what I say.
No,
the projected baseline.
It could be only the ground-based antenna also is 10 meter. Then you are right. But if it's large,
okay.
Yeah, but that's resolution. No, resolution.
Yes, it's large.
Resolution is determined. Resolution
by diameter of single dish.
No. Sensitivity is determined by diameter.
And also,
but resolution of interferometer is determined by the distance between the antennas.
Of course, but how long it takes?
Fight.
What? How long it takes?
How to say the period is around 9 days.
To feel the
It's around 9 days is the orbital period. Okay. Just check at the site. It is written.
what is the limiting the size of beam for maser? You mentioned that about the prospects of very huge interferometry, they have no future because of the beam is narrow.
No, I didn't say so.
What is the angle of the beam of masers for space masers?
For different masers, it is different.
Please provide us with different knowledge.
Oh, different. So the estimates are very much different from 10 to -4, for example, of 10 to -4.
10 to -4. Yes, it means that half a minute or about so that's rather wide.
But sometimes. But this is for galactic mesons. If we have mega mesons in external galaxies, which I didn't mention here, I just noted that we detected it in external galaxies. Yeah, this is not known at all. They can be much smaller. But in fact, the sizes of the spots in these external galaxies of mega mesons is determined not by the intrinsic things. It is determined by the propagation in an intergalactic medium, and this is determined through scintillation. It tells that it is about 10 microseconds. But
then could you repeat, because I couldn't understood properly, didn't understand properly. What is the limit for size of interferometer you talked?
What is
in your talk, you said that the size of the interferometer baseline, of course, couldn't be too long, very long, because you miss the view of the.
You can miss.
You can miss.
No, but that's what I told you. That we can miss, but we didn't do this. We detected fringes. So some people, and you've heard this, that some people say that, oh, the beaming is too high. You will not detect anything. That, for example, even parts of our team members who are responsible for mega mesons, they said that, no, that's not possible. That's possible. We've detected this. And this tells us that we have to change our understanding of the scattering in the interstellar medium, because we are detecting signals from very distant sources, which is not supposed, and they are situated just in the plane of the sky, in the plane of the galaxy. So the scattering should be very huge and should happen on very small time scales, but we see them. And that's one of the greatest achievements. And another scattering is scintillation, extragalactic things. We also see the signals on the greatest scale, on the greatest baselines. That means that this method, it has future. Yeah, it is possible. And what I've told you today is not the astrophysics. This is just achievement. This is technical achievement that we can do this.
Yes, sir.
So you mentioned the two-grid model to explain the light profile you observed. Did you try to reproduce this light profile in terms of any hydrodynamical model? Let's say you put some two grids in your box and then just calculate the light profile.
No.
Why not?
Why no? Because we have no time for this. So this is one of the things which is going possibly will be done in future. At present, what I'm saying, this is technical achievement. You see the things, and we are talking about botany or about firm facts. This is observational fact. That's what we see. And after that, one says, "Can you explain this?" Yeah, there are some explanations. Yeah, this is one possibility. I don't insist that it is correct or incorrect. I just say that it is possible.
More questions? No?
How many sources of the sky are there for the radioastronomy? And could you predict this number for the future with your own wish?
Можно по-русски?
I could repeat this. Сколько источников на небе для радиоастрономии видит?
So there were observations of about 20 or 30 sources. Yeah, you should understand that it is really difficult and challenging to get time for this. Yes, and so these many sources are detected. These are galactic sources. You see, out of 30. Another story is that what I'm trying to say once again, it's a great technical achievement, because now we are detecting the fringes for the sources, which were thought that there are no fringes, because now we know much better the procedure, how to process, how to correlate the signal. And you know, it is funny, but now we know the orbit of the satellite much better than we knew that 1 year or 2 years ago. So the recorrelation now
What is
gives
the
us
position accuracy now?
uh,
The position accuracy that you told just now.
yeah, but it's only not only position, it's also velocity and so on.
Yes. What is the accuracy of the positioning and velocity of the spacecraft?
I'm not that sure.
You told that it's much better than.
I know that it is better. I know that this detection was missed. It was missed.
It was a problem.
And the recorrelation brought out this source. That's it. So even now, we don't really have good statistics. And you should understand that, for example, if we get the data is measured in many, many terabytes. To collect it in one place, we need a couple of months just transfer of information from different antennas on the ground. Then they are correlated. Correlation takes 1 week.
So that's in the interferometric mode. That's my opinion. It's just my personal. You have enough main sources we observe because of these problems with time. And but the single issue, of course, you could.
I mean, the principal problem is you have to verify brightness temperature to observe the source. Otherwise, you just cannot observe.
No.
Not in terms of time.
No. We can detect the source readily if it has the flux density is higher than 15 joules. It's a tens of sources.
That should be very right. That should.
Look, I had no time to show you that the detection depends on if you use one small projected baseline. For example, yeah. So if you have longer, that's a lower possibility. So if you are asking how many sources which we can detect with a 9.5 Earth diameters, we'll tell you that these observations were not carried yet. We don't know.
Andrei, suppose you use simultaneously GPT 100 meter and TIFR 100 meter.
Yeah, we are doing this.
In this case, your base is 10 times, about 10 times shorter, but your sensitivity is 10 times higher. Maybe it's possible to get similar results.
Yes, we have, how to say, Effelsberg and GPT at the same time. But there are some here. But it's a big problem that during this session, GPT was working, Effelsberg was not working. And in the other, we have, for example, we have 1 hour in a year. And this hour is failure or something like blackout in the US when they didn't give GPT time. But the source is visible 1 hour in a year. Because of this funny orbit and so on. So the source is visible 1 hour. And you need all these telescopes to be placed in the proper places and to have very good conditions. We are facing very big problems right often. So during this session, Effelsberg didn't get any fringes. It was not working properly. The system.
So that's, I think that we had today a very fruitful session, interesting. Thanks a lot for all the speakers and all the people who raised questions. Thank you very much. Yes, some announcement from organizing committee.
So, there are some corrections to the program which was on the conference site. I think first, I think that we can start tomorrow, not at 9, it's announced in the online schedule, but probably we can start, say, 9:30. Just shortening the lunch break, because I guess we don't need 1 hour. Will be okay. Then some participants could not arrive, in particular Vasiliev, and so they will make some another changes to the program, which will be shown in the new version of the program tomorrow. So
So now it's finished. So we begin at 9:30. Yes. So it's, if you need to watch my session, but please come a bit earlier to elevator. Yes. To download, to check, to get the process and so on. Okay. Cool. Which place? It will be here or...
В общем, всем спасибо за просмотр. Тут сейчас некоторые организационные моменты нужно уже закончить, потому что, ну, в принципе, уже будет неинтересно. А оттуда, наверное, с другой комнаты. Так что всем спасибо за замечание. Че? Да, всем спасибо, кто смотрел.
Спасибо. Завтра будет интересно.
Да, завтра будет интереснее, скорее всего, будет налажена связь получше, поэтому ждем вас завтра на этом же канале. До свидания.